Hi everybody, I wish I could be with you all today in class. Unfortunately, you're going to have to deal with me remotely today. Today I'm going to teach you about detection limit. By the end of my lesson here, you should be able to define it, or at least explain what it is, and calculate it two separate ways. So there's the dictionary definition for it, but to put it in a nutshell for you, depending on what experiment you're doing, it is the smallest amount of analyte, whatever it is you're trying to measure, that you can detect and say it's definitely there. You might not be able to quantify it and say how much is there, but you can definitely say, yep, it's there, it's in that sample. And depending on what you're doing, there's going to be different detection limits. So if you were using something from like our balances, their detection limits might be, they might be able to measure a hundredth of a gram. That would be the lowest thing that they can detect. Is it really a hundredth of a gram? I don't know, but it knows something's on there if it's measuring that. Okay, so as we've learned in this class, there's always error with any measurements. I'm going to use the spectrophotometer as my example of that. If you guys don't know what that is, it's the machine on the sides of the room. There's a few of them. You put a little glass cuvette in there, and you can put a solution in there. It shines light through it, and then there's a detector that will absorb or measure how much light is passing through that solution. Well, if we just put in a whole bunch of blanks, just blank cuvettes with pure distilled water, you wouldn't get every reading to be zero. You would see some noise. Some of the absorbance might be like 3, 2, 1, maybe a -1, I don't know. And that might be because, well, the cuvettes maybe, they're not formed exactly the same. There might be some imperfections. There might be a fluctuation of electricity going into that detector. There's a bunch of things that can make machines error. But we call that range noise. And typically what we do is we'll take an average of that noise and get a baseline from it. We can also look at the data that's in that noise and get a standard deviation from it the same way we would with any collected data that we'd have. All right? So once we figure out what the noise is, I think I might have skipped the slide there. Or maybe not. Once we figure out what the noise is, we can actually analyze that data, multiply the standard deviation by 3, in most cases multiply the standard deviation by 3, and get the detection limit. The reason we multiply it by 3 standard deviations, if it's normally distributed, 99% of the data should fall in that range. So all of a sudden, if you're outside of 3 standard deviations, there's a good chance that it's actually showing something in that sample. It's a pretty good determination for detection limits. So some machines just use that method. They can do it in real time. This machine is an HPLC, high performance or high pressure liquid chromatography. The way it works, you inject a liquid sample in there. There's a bunch of coils in there, and inside the coils there's little beads that are packed in there. And depending what's in that liquid, some of the stuff sticks to the beads more than other things are going to stick to those beads. And when it comes out of the long coil, the stuff that doesn't stick as much comes out first. The stuff that adheres a little bit more comes out later, and this machine measures it. If you've done the old chromatography where you put maybe a black dot of ink, some alcohol on the bottom, and it raises up the paper and all the colors come out, that's very similar. That's just paper chromatography, but this machine runs the same way. Well, if you're sending blanks through it, this can measure data in real time. A lot of this stuff is automated where it can actually, it'll know the detection limits. So it can analyze those numbers in real time, calculate the noise, give you 3 standard deviations above it, and that would be our level of detection. If you wanted to quantify it and actually put numbers to it, they usually want it to be about 10 times at least above that noise ratio. So quantification would be if Demontra, you won a gold medal in swimming, and your steroids comes back at so-and-so micrograms per liter of blood, and you're 10 times over our noise. Now all of a sudden I might be able to say, hey, you have this much in your blood, versus Lilith, who I could just say, yeah, you just got a little bit in there. I don't know how much, but we detected it. So there is a difference between limit of detection and limit of quantification. The biggest part of that difference is how far away are you going from the noise in terms of standard deviations. All right, so how do we calculate the noise and how do we calculate the standard deviation? That's pretty easy. If we were going to do it with the spectrophotometer, like I said, we would measure maybe 20 blanks, put them all in there, record the absorbance just from distilled water. We could plot that out in one of our data tables. After we get those 20 numbers there, I could hit equal average, it's going to spit out an average. I could hit equal standard deviation, it's going to spit out the deviation, and I could just multiply it by 3. And we would have our limit of detection that way. There is a problem with this method. Can anybody think of the problem with detecting noise this way? Julia, I see your hands up. Do you know what it is? Very good. It would be time consuming. Yeah, we don't want to sit around and be measuring 20 blanks and not have to, actually, that'd just be a waste of experimental time to me. So there is a quicker way to do it. And the quicker way is using our calibration curves. I will show you guys a calibration curve in a second, but typically what we're going to do is we're going to take that calibration curve. We're going to need a couple things off of it. We're going to need where it intercepts the y-axis. We're going to need the 3 times the standard deviations of our data. And we are going to need the slope of this line. We usually use, mx plus b, but they actually have a b on here. So this line for the equation is going to be b. And I know the intercept's usually b, but it's going to be a on this one for when you guys see the data. The other thing too is that we could also use the standard error. Standard error, it depends on the type of distribution you have. Using normal distribution, I like to use the 3 standard deviations because 99% of the data is falling in there. But occasionally you won't end up with a normal distribution for some of your data collection. You might end up with some sort of a curve where the formula is a little bit different than linear, but you can still look and find out where most of the data falls between. And to get your standard error, if you wanted to, you could look at the average from here and then the distance, the range where most of the points fall within there, and you can get it that route. So back to calibration curve. These are easy to make. They don't have to be concentration, but we do these a lot. So for example, spectrophotometer. I would make some solutions of known concentrations. I would, weigh out the powder. I'd know how much water's in there. I'd put them in the machine. I'd record their absorbance. And that's all the little dots. You can barely see them on here, but they're on there. And they don't all perfectly fall on the line, okay? Then using your software, you could get a line of best fit, which is going to have your slope and your intercept. In this case, the intercept is 0. That's not always the case. And the reason we use calibration curves, since we're using that piece of equipment, when we do our experiment, if we get a solution that's measuring 0.684 absorbance, I could go to 0.684 absorbance, follow this over to my calibration line, come straight down, and I can get my concentration from there. So we typically make these lines, and we use them to get our experimental data. Why not use them to get our limit of detection? So just to show you before, when you do a calibration line, your intercept may not be 0. I just wanted to bring up that it could even be in the negatives as it is in this case. All right, so we are going to need that intercept. We're going to need the slope of this line. And the other thing we're going to need is either a standard deviation of our data, because we're going to need to multiply that by 3, or you could use standard error. So back to that original diagram that I have here. So this would be your calibration curve. You got your points all over it. When you find your intercept, okay, you are basically going to add 3 standard deviations above this. So you have your intercept and your 3 standard deviations above it, and that is basically going to give you the y-axis value where your limit of detection would be. If you take that y-axis value, take it over to your same line that you used, your calibration curve, and go down, this, if it was a concentration, that would be your limit of detection. So you could do it straight off the graph, or you could calculate it mathematically. So since we're basically using the slope here, rise over run, you could take your